Chapter 6, Volcanoes and Other Mountains. In Chapter 6, we'll discuss the volcano commandos, magma viscosity, magma sources and magma composition, the Mount St. Helens eruption, products of volcanic eruptions, volcanoes and volcanic landforms, mountains, why are they there, and the rise and fall of mountains and temperatures. As a scientifically literate citizen, what 3 questions would you ask about this volcano if you moved to the city in the foreground? The city is Tacoma, Washington. I used to live there. This is Mount Rainier. There are 1,500 active volcanoes worldwide. A third of these volcanoes have records of previous eruptions. There are 2 or 3 eruptions per decade that are major disasters. Over 500 million people live near active volcanoes. Fewer than 200 volcanoes have instruments to assess the potential for eruption. Volcanic mud flows from the eruption of the Nevado del Rios volcano in Colombia killed more than 23,000 people. The geologists of the Volcano Disaster Assistance Program help identify risks of potential eruptions. 9:08 p.m. Eruption from the summit. Snow and ice melted and mixed with debris from the eruption to form mud flows that moved downslope and filled major river channels. 11:30 p.m. The mud flows reached Armero at the mouth of the canyon, 74 kilometers, which is about 46 miles, away from the volcano. Look how tiny the houses are right here and how you can see the flow, the lava flow. Buildings were carried away or buried by mud flows up to 5 meters deep, which is about 16 feet. Not lava, mud flows. Distribution of older lava flows gave scientists some idea of the potential eruption products. Scientists traveled to Congo to examine the eruption of the volcano of 2002. The lava flowed through the nearby city of Goma, which has 450,000 residents. Fortunately, the toxic volcanic gases trapped in Lake Kivu were not released. Poisonous volcanic gases from the Lake Nyos in Cameroon killed 1,700 people in the surrounding villages in 1986. The escaping gases drive the volcanic eruptions. How easily gases escape from the magma is controlled by the magma viscosity. The magma is molten rock below the surface, but when it comes out of the volcano, it's lava, molten rock at the surface. The viscosity is resistance to flow. The amount of viscosity depends upon the temperature and the magma composition. The magma composition varies with plate tectonic setting. Viscosity is resistance to flow. The viscosity of materials decreases with increasing temperature. The viscosity varies with composition as well. So air has a very low viscosity compared to corn syrup. Tar has a higher viscosity than canola oil or water. The escaping volcanic gases drive the eruptions. Gases are dissolved in the magma. Water vapor, carbon dioxide, sulfur dioxide, and the pressure on the magma decreases as the magma rises toward the surface. The gases are released as pressure decreases. Think of a carbonated drink. It works very much like that. The gases get released as the pressure decreases. When you open the screw top of a carbonated drink, it makes a noise. It goes shh. That's the gas being released. The viscosity depends upon the magma composition. Silica content. Silica is a combination of oxygen and silicon that combines with other elements, for example, sodium and potassium, to form minerals. The elements combine to form simple structures in minerals. The ones with less silica has a lower viscosity. Elements combine to form more complex structures in minerals with more silica means it'll have a higher viscosity. Viscosity depends upon magma composition or the silica content. For instance, these three types of lava, the basalt, andesite, or rhyolite, have a different viscosity. Basalt is low. Andesite is a medium type. And rhyolite has a very high viscosity. If the temperature is higher, it has a lower viscosity. If the silica content is lower, it has a lower viscosity. Mount St. Helens, Washington State. More viscosity equals more violent eruptions. Gases escaped easily during mild eruptions with low viscosity. For example, the magma below Mount Kilauea in Hawaii. Gases escape explosively from high viscosity magma, for example, Alaska. Is this a mild or a violent eruption? I'd say that was a little bit more violent. Certainly not Mount Kilauea, where it just kind of bubbles out the top and flows down the side. If it's more viscous, the eruption is more violent. Most active volcanoes are found near convergent plate boundaries. Others associated with divergent boundaries, like in Iceland or East Africa, form above hotspots. Different plate settings generate magma from melting different sources of rocks. Heat from the rising magma melts some of the continental crust to form rhyolite. And when water is driven from the subduction plate, it causes a partial melting of the mantle. A basaltic magma, a partial melting parts of the asthenosphere below the ocean ridge or hotspots. It also occurs at the continental divergent boundaries and hotspots. Rhyolitic magma is melting of parts of the continental crust. Different plate settings yield different magmas from different source rocks. Oceanic hotspots has basaltic magma. Like I said, I was able to pick up a piece of basalt and hold it in my hand when I was on the Big Island in Hawaii. Also on Maui, any of the islands, actually, you would be able to find basalt and ancient lava flows because they're formed from volcanoes. At a divergent boundary in the oceanic ridge, basaltic magma is found there. It's also found at divergent boundary where there's continental rift. Rhyolitic magma is also found there. Look up the big crack in Africa that has occurred in the continent. It's quite interesting. Google it, see what you find. Andesitic magma, a partial melting of mantle rocks with water, occurs at subduction zones. Different plate settings generate magma from melting different source rocks. Silica content is controlled by partial melting of rocks at the magma source. Partial melting occurs when some minerals in a rock melt while others remain solid. Think of perhaps making a cake and you're using a different type of flour. Maybe you're using coconut flour and almond flour. They have their consistency is a little bit different. You must sift them. If you don't, you'll end up with lumps in the cake. Well, the different minerals represent the lumps in the cake, the different types of materials that are in there, and these will remain more solid depending upon what type of mineral it is. The minerals with the lowest melting temperatures will melt first, and the silica-rich minerals have the lowest melting temperatures. Partial melting generates a more silica-rich magma than the parent rock. There are 3 types of magma that are defined by the silica content. Partial melting of the asthenosphere generates basaltic and has a low silica content. The mantle wedge has andesitic magma with an intermediate silica content. And the continental crust has rhyolitic magma with a high silica content. So different magma types form in different plate tectonic settings. The Mount St. Helens eruption. The Cascade Mountains. The Cascade Mountains. Volcanoes formed above subduction zone where the Juan de Fuca plate slides beneath the North America continent. Mount St. Helens is the most active volcano in the continuous U.S. In early March, the unrest that was featured, there were minor eruptions, there were earthquakes, there was a release of volcanic gases, and this was followed by a change in the shape of the cone, the bulge. And there was an increased frequency of the earthquakes that were occurring. The magma began to rise. As it rises, it pushes up. The debris avalanche breaks free. A lateral blast expands as landslide blocks the slide, and it slides down slope. Vertical eruption column rises up to 20 kilometers, which is about 12 miles, within 10 minutes of the initial eruption. Look how much is gone. May 18 eruption. A moderate earthquake triggered a massive landslide, the debris avalanche on the north side of the volcano. The debris clogged the streams. The pressure released on near-surface magma. A lateral blast produced an initial sideways eruption to the north, and later a vertical eruption. The Volcanic Explosivity Index measures the volume of erupted material. There are 8 divisions on the log scale, which increases by 10 times each division. Mount St. Helens VEI rank is a 5. Major products of volcanic eruptions: the airborne, the lateral blast, the tephra, the volcanic gases, the flows on the land, the lava, the pyroclastic flows, the lahars. The eruption of Mount St. Helens reduced the height of the volcano by 400 meters. Remember, the whole north side was blown right off the mountain. The features near the volcano were blown over or carried away by the products of the eruption. Geologist David Johnson died at this site on Johnston's Ridge, which is located 10 kilometers from the volcano. There he is. 10 kilometers from the volcano. Look at the difference in the mountain from before the eruption and after the eruption. Before and after. Same location. Rare lateral blasts can destroy objects up to 12 kilometers away and knock down trees more than 25 kilometers. The effect of a lateral blast only seen on the north side of Mount St. Helens. See, here's Spirit Lake. Here's the crater, and look toward the north where all the material flowed. Pretty incredible. Tephra represents particles that are blasted into the air by eruption. Volcanic bombs and ash are found near and far from eruption source, respectively. These are blobs of magma which solidify into lava bombs. So depending on how far they are, that's the size. Wind can transport fine volcanic ash for hundreds of kilometers. So it would have blown toward the north and probably toward the east, since that is the direction the weather travels in general. So once it landed, it was carried even farther. The Mount St. Helens eruption compared to the Yellowstone eruption 640,000 years ago. Look how large the Yellowstone eruption was and how far the ash was spread, way over by Texas. Tephra represents the particles blasted into air by the eruption. Volcanic ash, the particles of less than 2 millimeters in diameter. Its measurable ash deposits were found hundreds of kilometers from the volcano, halfway across the country. Compare Mount St. Helens ash fall to the Yellowstone supereruption of 640,000 years ago. Mount St. Helens was much smaller. Trees were killed by excessive carbon dioxide released by the magma under Mammoth Mountain in California. Volcanic gases such as water vapor, sulfur dioxide, and carbon dioxide may affect climate patterns. Sulfur dioxide may block insolation temporarily up to a year, reducing global temperatures. Widespread release of carbon dioxide and higher temperatures due to faster rates of volcanic activity approximately 120 to 80 million years ago. There are eruption products on the land. Check this out. You can see this is lava flowing down the mountainside right here. If you were in Hawaii, you could see that. You've probably saw on television lava flows from Kilauea, which is after this photograph was taken. You've probably seen the lava flowing right over houses and destroying them. Yes, you can walk on the lava. I've done this actually in Hawaii. Low viscosity lava can flow up to 50 kilometers from its source. Lava transported to front of lava flows in long lava tubes. The lava flow builds up in a series of layers. It cools off and solidifies. Eruption products on land. Higher viscosity lava remains within the volcano crater. The lava dome formed in crater of Mount St. Helens right here. This little section, see where that blast is coming up right there? That is this photograph. And here's a drawing of what's happening. Ash and volcanic gases are escaping. Pyroclastic flow. A dense cloud formed from the combination of tephra and volcanic gases. And it was really fast moving, and it was up to 700 degrees Celsius. This is one of the problems with the eruption in Hawaii, were the volcanic gases that were in the air, and still are actually. Every once in a while it's pretty bad. It's very toxic. Lahars, which are mud flows that are formed when volcanic debris mixes with streams or melting ice. They're often confined to stream channels. The lahar along Muddy River reached depths of 20 meters following the Mount St. Helens eruption. Here's Mount Rainier and a map of the lahar hazard and how far the lahar could flow. There are three types of volcanoes: shield, stratovolcanoes, cinder cone. They are composed of different materials. Each volcano type and eruption style varies with the plate setting, and each is a different size. Shield volcanoes. For example, in the Hawaiian Islands, they're broad. They have gentle slopes built from many low viscosity lava flows. They have relatively mild eruptions that are associated with hot spots, divergent plate boundaries. Stratovolcanoes, for example, Osorno in Chile, is the most common volcano type. It has steeper slopes built from alternating layers of tephra and medium viscosity lava. They're made out of andesite. They form on plates that override subduction zones at convergent plate boundaries. Cinder cone volcanoes are the smallest volcanoes. They rise up to 400 meters in elevation. They are built from more viscous magma products, very coarse tephra. They may form on slopes of shield or stratovolcanoes. Sunset Crater Volcano in Arizona. Other volcanic landforms, a caldera, such as Yellowstone. A giant crater formed from the collapse of a volcano into underlying magma chamber, for example, Yellowstone, Wyoming. The brown represents the basalt flows. Other volcanic landforms, a lava plateau. Hundreds of low viscosity lava flows stack up on top of each other. The individual layers of basalt can be 10 to 20 meters thick. A plateau is thousands of meters thick. It forms from some of the largest volcanic eruptions, the Columbia River Plateau. A lava plateau. See where they're located, all these red areas around the world. A massive basalt eruptions formed lava plateaus and elevated atmospheric levels of carbon dioxide from 120 to 800 million years ago to produce global hothouse conditions. Geysers, hot springs, fumaroles, and mud volcanoes. These form whenever water circulates near a magma chamber. Geysers, and the most geysers in the world are located in Yellowstone Park. Geysers are when water is heated under pressure with volcanic gases. A hot spring is heated groundwater rising to the surface. A mud volcano is chemical reactions converting rock to clay. A fumarole is when volcanic gases escape in the absence of water. The thickest crust found below mountains along convergent plate boundaries. The Himalayas, 70 kilometers thick. The Andes is up to 60 kilometers thick. And normal crust is about 40 kilometers thick. The higher, younger mountains are along the present convergent boundaries, for example, the Himalayas. And the lower, older mountain belts represent ancient convergent boundaries, for example, the Appalachians. The Appalachian mountain chain is far older than the Rockies. Why are they there? It has to do with the plate tectonics. Ocean-continent convergence. Continent-continent collision. Reverse faults stack up and thicken the crust along convergent plate boundaries. Additional thickening of crust occurs where the northern margin of the Indian continental crust is wedged below the southern margin of Eurasia. What would happen if we used a block of oak with a density that is 80% of water? Well, density is mass per unit volume. In other words, how many molecules are there in a specific amount of space? The density of water is 1 gram per centimeter cubed. The density of pine wood is half a gram per centimeter cubed. Wood floats because it's less dense than water. The density of pine is half the density of water, so it rises above the water. Half of the pine block lies below the water surface. the density of oak is 80% the density of water. 80% of the oak block lies below the surface. Smaller blocks don't float as high, but they don't extend as far below the surface. Much of the difference in the size of the blocks is in the submerged root. Changes in elevation depends on the relative density of crust and mantle. The height of wood blocks and continents will decrease or float lower as the mass is removed. The height of wood blocks and continents will increase or float higher as the mass is added. The elevation only changes by 20% of the added or removed material. Most changes occur in the crustal root, which is below the surface. The rise and fall of mountains and temperatures. If you remove one layer, the elevation is 16 units. Remove 5 layers, or 100 units, the elevation would be 20 units. This is for oak. If you add a layer, the elevation will be 24 units here. Here's a graph that shows the difference between the region that erodes into the mountains and deep valleys, and the region that erodes almost uniformly downward. For every 1,000 meters of rock that's eroded from the mountains, isostasy results in just 200 meters decrease in elevation. 800 meters of change is accommodated by raising the crustal root. Its evenly distributed erosion causes uniform lowering of mountains. The erosion, which is concentrated in the valleys, can cause the peaks to become higher. Mountains are very long-lived features on Earth. The still-forming Himalayas, that's right, still forming, Mount Everest is growing every year. I'll give you that it's growing only centimeters, but it is growing. The Himalayas began to form about 50 million years ago, and the lower Appalachian Mountains formed about 300 million years ago. The approximate erosion rates are 0.1 to 0.2 millimeters per year. The rate depends on the rock types, the climate, and other factors. It takes 5 to 10 million years to erode 1 kilometer of rock. But isostasy will replace 80% of the erosion. 200-meter change in elevation occurs every 5 to 10 million years. Between 25 and 50 million years to lower a mountain by 1 kilometer. Mountain ranges will persist on the landscape for hundreds of millions of years. The erosion of the Himalayan mountains. Warm, moist air from the Indian Ocean rises over the Himalayas to form monsoon rains, the rain that feeds the rivers that erode the mountains. Sediment deposited in the Bay of Bengal and the Arabian Sea mountains influence climate patterns. The monsoon rains strips the carbon dioxide from the atmosphere. The removal of CO2 has been going on for 20 million years. This action actually reduces the greenhouse gas. And the reduction of the amount of greenhouse gas has lowered the global temperatures by about 5 degrees Celsius. So without this particular greenhouse gas, we would be warmer by 5 degrees. This is showing the monsoons.